行，
哎，等会儿，我拿手机看，我突然想到我自己看不到演讲稿。
拿手机看啊。
对好，Hi Mike, thanks for taking the time to review my submission for M5 Final Hackathon. I'll walk you through my show prediction model, focusing on how we ensure interpretality, fairness, and responsible AI principle while achieving strong predictive performance. For this challenge, I built a meta model ensemble that combines multiple classifiers like random forest, XGBoost, LGBM, and CatBoost. Instead of relying on a single model, I train each classifier independently and use logistic regression model as a meta learner to aggregate their predictions. This approach significantly improved accuracy, giving us an F1 score of um, 82 on the validation set. But accuracy alone isn't enough in healthcare, where this model could be used for real-world decision making. Transparency and fairness are just as important as performance. Done.
The second part is fairness and bias detections. To ensure the fairness, I ran several bias detection tests to check whether the model treats different demographic group equability. One of the most critical metric is AUC, area under the curve, for male and female patient, which help us to measure whether the model is equality accurate for both groups. And the result is AUC, area under the curve for female patient, which is 0.78, and area under the curve for male patient is 0.80. Since the scores are close, we don't see a major performance bias, but I also check the demographic parties, ensuring that the model practice stroke at similar rates across groups. This model predicts a stroke for 32% of the females and 36 of the males. This small gap suggests a slight imbalance, but is within an acceptable range. If these differences were larger, I would consider rebalance the training data using the rewriting techniques or adjusting the decision threshold for different groups. And model interpretabilities. A big part of this hackathon is make sure our models aren't black boxes. To explain how my model makes decisions, I use the three interpretability techniques, um, SHARP, LIME, and anchor method. The first one is Sharp, understanding feature importance. Sharp help us to understand which feature drives the model's prediction at both the global and the individual levels. Looking at the Sharp summary plot, the top three most influential features in stroke prediction were: first one is age, Sharp value, which is plus 0.42. The glucose level, Sharp value, which is plus 0.31, and the BMI is Sharp value is plus 0.27, which means that the age plays the biggest role in determining stroke risk, followed by glucose and BMI levels. For individual cases, we see similar trends. For example, in one case, a patient's age contribute plus 0.45 to fan prediction, while a low smoking status reduce their risk by minus 0.18. This aligns with the medical knowledge, but also raises the questions. Is the model over-relying on age?
The second method is line. Um, it gives us another way to understand how different features contribute to predictions at an individual level by slightly altering inputs and measuring the impact. For a specific patient, LIME found that the age is plus 0.38 and BMI is plus 0.22 and the work type is negative zero point 0.1. Interestingly, the model assigned a negative contribution to work type, suggests that employment individual might have a lower prediction stroke rate. And this might be the data-driven patterns, but it could be also indicate that hidden bias that should be investigated further. And the lastly is the anchor method. If then rules the explainability. The anchor method provide human readability decision rules, allow us to generate a then statement that explain individual predictions. Here are the case where the model predicted stroke. The first instance is the predicted mali- malignant. The rule is the smoking status is higher than 2, and the coverage 40%. And the second is the rule that age is less than 57 and coverage the data of 77%. Since the age is less than 57, rules appears twice. This tells us the model is heavily prioritized age in its predictions. While this may be reasonable from the medical standpoint, we need to be careful. It could lead to age-related bias if other health risk factor aren't sufficiently considered. The smoking center rule has high precision, but only applies 14% of the cases, meaning that it has strong but rare condition in the data set. In summary, our meta model ensemble delivers strong predictive performance, and our fairness analysis confirmed that the model does not exhibit significant gender-based bias and SHAP-LIME analysis confirmed that age, glucose levels, and BMI are the key factors driving predictions, and the anchor method highlight the model reliance on the age-based decision rules. However, the reliance on age raises important ethical considerations. Moving forward, I will explore fairness-aware machine learning techniques to ensure that the model does not disproportionately impact certain demographic groups. Additionally, I would validate our models, decision logic, and medical expert to ensure that the explanation align with real-world data, clinical knowledge. Thank you for your time, Mike. I appreciate the opportunity to participate this hackathon, and I would love to hear your thoughts.
Okay.